Thank you for joining us today for the Precision Medicine and Population Health webinar on using genetic risk scores in the prevention and control of common diseases, opportunities, and challenges. Before beginning our presentation, I would like to provide a few tips for using WebEx so that you get the most out of today's webinar. Attendees will be in listen-only mode. Please feel free to submit your questions throughout the presentation in the Q&A panel and select all panelists from the drop-down. Our moderator will ask the questions on your behalf during the Q&A portion of the webinar. If you need live captioning, please refer to the chat panel and a link will appear shortly. I want to note that today's webinar is being recorded and will be posted online at a later date. I would like to introduce our moderator for today, Debbie Nguyen.
Thank you. I wanted to let you know that today's webinar is hosted by the Precision Medicine and Population Health Interest Group in the Division of Cancer Control and Population Sciences at the National Cancer Institute, which is where I am from. It's also co-sponsored by the Center for Translational Research and Implementation Science, National Heart, Lung, and Blood Institute, and the Office of Public Health Genomics, Centers for Disease Control and Prevention. Dr. Muin Khoury is here today, and he will be leading the question and answer session. Most common diseases, such as cancer and heart disease, are caused by a combination of genetic and environmental factors, and the genetic components can involve multiple genes. There's been a recent surge in scientific interest in publications using genetic risk scores to stratify people by level of risk and explore information in prediction, screening, and control of common diseases. Using cancer and heart disease as potential applications, this webinar will explore findings, genetic opportunities, and challenges in using genetic risk scores in prevention and control of common diseases. We have two great speakers today. The first will be Dr. Sekar Kathiresan. He is the director of the Center for Genomic Medicine at Massachusetts General Hospital in Boston and director of the Cardiovascular Disease Initiative at the Broad Institute and associate professor of medicine at the Harvard Medical School. He'll be talking on using genetic risk scores, prevention and control of common diseases, pressing opportunities. Dr. Cecile Janssens will be talking second on using genetic risk scores in prevention and control of common diseases, scientific and implementation challenges, professor of epidemiology at the Rollins School of Public Health at Emory University in Atlanta. If you'd like to tweet during this webinar, please use hashtag GRSwebinar. And with that, I will turn the presentation over to Dr. Kathiresan.
Okay, can you okay? Wonderful. Thank you so much, Debbie, and thank you, Muin and Cecile, for the opportunity to discuss polygenic risk scores. Let me jump right in. So with a healthcare scenario, this is a 42-year-old male who presented with dizziness and profuse sweating, had called an ambulance, and what you read here was that the patient was ready for transfer from the chair to the stretcher. He started posturing and having a seizure, and then subsequently was transported to the ambulance unit. One unit, the patient went into cardiac arrest, which is the rhythm strip that you see here, and was resuscitated with a shock. And then see down low the first rhythm, which shows the evidence of an inferior ST segment elevation, myocardial infarction, or heart attack. The patient had the acute coronary blockage treated, but unfortunately had suffered a fair amount of anoxic injury during the resuscitation, died 10 days into the hospital course. You have an example of a 42-year-old male with fatal early onset myocardial infarction, and his high risk factors, probably the event, are shown here in terms of the cholesterol profile, the blood sugar, body mass index, and so forth. And what ends out is his LDL cholesterol is actually fairly average, but his HDL is a little low, the triglycerides are a little high, and he has family history with a father with a myocardial infarction at age 54. Now, we typically see these patients in clinic. We're asked to assess risk for myocardial infarction using a global risk score. Next slide. And we have risk scores called the American College of Cardiology, American Heart Association cohort equation. And this estimates one's 10-year risk of having atherosclerotic cardiovascular disease, ASCVD. And for this patient, if you put in the information, his risk factors prior to the event, i.e. that he comes out of 10-year risk of 1.7%. This is considered low risk, and the patient would not be recommended for a medication like statin to reduce risk of heart attack. Why is the AHA pooled cohort equation not useful in young people? And that's because the model is almost entirely driven by age. And that makes sense because if you take a population, the older you are, of course, the more likely you are to have a heart attack. So it's actually very unusual for any young person to have risk that's enough to warrant or have statin treatment recommended. So the scenario that I'm going to address, and this is taken off of that Cecile has put out in terms of how to think about prediction in a prediction research manual, and 4 issues to think about. What is being predicted? What is the intended target population? How are we doing the prediction, and what purpose? And here we're looking in terms of risk for myocardial infarction. I'm going to focus on men and women before the age of 55. So, because I'm interested in premature myocardial infarction and looking at that. We're going to predict using a set of gene variants and for what purpose. And here the main decision point is statin initiation. These are cholesterol-lowering medication initiation at an early age. Onset disease, as I mentioned, the global risk calculator for heart attack doesn't work at all. And so stratifying individuals based on DNA variation is another option because most diseases have an inherited component, and the inherited component often plays a much larger role in early onset disease. And so we've explored over the last 10 plus years how to stratify individuals based on DNA variation, stratify individuals for risk for myocardial infarction. If you have the inherited component to early heart attack, there are basically 2 major models. Monogenic model, where a single mutation is sufficient to lead to early disease, and a polygenic model, where the additive effect of many variants may contribute to early onset disease. And we'll explore each of these models. For genetic prediction, it focuses on rare monogenic mutations. And so the classic example for heart attack is familial hypercholesterolemia. These are mutations in any of 3 genes, LDL receptor, ApoB, PCSK9. These mutations, the carriers have higher level of blood LDL cholesterol, and they're on average about 3-fold increased risk for heart attack. And this model is operative in about 0.4% of the population. That's the carrier rate, so less than 0.5%. It's well accepted that it's useful to find this risk group early in life and to get LDL-lowering medications to this group, particularly statin medications, to reduce their risk of heart attack. And early initiation of statins in this group can markedly reduce their future risk of events. Next is compelling to screen for this mode of risk, and to the point where it's deemed a Tier 1 genomics application by the CDC. So testing for familial hypercholesterolemia mutations is supported by clinical practice guidelines, and as a result, the CDC has deemed it a Tier 1 indication for screening. Now, and our question was, can we identify patients similar risk to monogenic variants, but identify based on a polygenic risk model? And work that we've focused on over the last 2 years. The concept of polygenic risk scores goes way back. Our first paper in this field is in 2008, about 10 years ago, where we looked at about 8 polymorphisms at the time and asked the combination of those, could they relate to the risk of disease? And so the models take polymorphisms, each of them carries 0, 1, or 2 copies of the risk allele, and a score ranging from 0 to 2n for each person, and you can additionally weight the score based on each allele based on the effect size on coronary disease. These scores have typically been constructed based on gene variants that exceed a genome-wide significance threshold. Shown at the bottom is a Manhattan plot, for the latest meta-analysis for genome association study for coronary disease. On the x-axis are the chromosomes, and the y-axis is the strength of statistical evidence. The straight line here is the genome-wide threshold, and there are 95 gene regions that exceed the threshold. And so you can score out of the top 95, and basically it does predict risk. But the new insight in the last 2 years is that there's actually much more information potentially, not just in the top of the list, but looking at the entire feature set from polymorphisms associated with risk. And so we have basically developed a genome-wide polygenic score. So moving from the top SNPs to a genome-wide set of more than 6.6 million for prediction. And this is work like I'm at Kara in the group, and the work is up on our archive as of late last year. So what do we get when we do this kind of approach? So again, the hypothesis is the polygenic score, including a genome-wide set of SNPs, can identify individuals' risk equivalent to a monogenic mutation. So what we did was, step one was take a training data set, which is the genome-wide association study, involving 60,000 cases, 120,000 controls, each varying as an effect size on coronary disease, and we take the 6.6 variants. We end up making several scores with different algorithms and test those scores in a validation data set of 125,000 people from UK Biobank, a prospective cohort study established in the UK in 2006 to 2010, involving 500,000 participants. Participants at baseline, 4,000 had coronary disease, 120,000 were controls, and this is the data set we used to pick the best score. Having picked the best score, we ended up moving to a testing data set of the remaining UK Biobank, about 300,000 individuals, independent of the two data set, and then applied for the best score to this testing data set. And I'm going to show you data basically from the testing data set. Distribution of the score across the 300,000 people. On the x-axis is the polygenic score, on the y-axis is the density. And what you can see is a beautiful bell curve, like any other quantitative traits in the population, like height or LDL cholesterol. And what we have here then is a number, a new quantitative metric of one genetic liability to heart attack. On hand, we can ask a few questions. One is, what is the gradient in risk across all of the different bins of a polygenic score? So on the x-axis are percentiles of polygenic score. Each dot represents a 1% bin, roughly representing 3,000 individuals, because the overall data set was 300,000. On the y-axis is the prevalence of coronary disease in each bin. And what you can see is there's more than a 20-fold gradient in prevalence across all of the bins, the percentile bins of score. Another to ask is the correlation of this score with existing risk factors. And so back to the ACC-AHA pooled cohort equation. On the x-axis here is the polygenic score. On the y-axis is the ACC pooled cohorts equation calculated for each person. And what you can see is the correlation coefficient is very low, so 0.02. And so very little correlation with current measured MI risk factors. This genome-wide score, polygenic score, is capturing something quite orthogonal to the things we measure every day in clinical practice. Model, can we identify a group with risk for MI equivalent to monogenic mutations? And so we ended up asking a thresholding question. So if you get the top 5% of the distribution and ask what their risk is compared to the remainder, what that folding in risk for the 5%. And this is so that we make this analogous to the Mendelian mutation analysis, where you can comparing a carrier with a mutation versus everybody else, all the non-carriers. And so we're essentially labeling the top 5% of the distribution here as a mutation carrier, quote unquote, and everybody else is non-carrier. And if you do that, what you see is that the conferred by the top 5% of score is equivalent to a monogenic mutation, is at 3.3 in this data set. And if you go to the 1% tail compared to the 99%, the risk is even greater at 4.7. So the top 5% of polygenic score risk is equivalent to monogenic mutations. But UK Biobank is a prospective cohort study, and there may be issues regarding selection of individuals, ascertainment, and they may be a little lower risk than the average population, plus they're in the UK. What about the US? So we look at external validation. And so this is unpublished data. We basically have now looked at the same score that was developed in UK Biobank and tested it in a case control set of 2,000 individuals with early onset MI in the United States and 3,700 controls. These are individuals hospitalized. Cases are hospitalized in the U.S. across the U.S. and they have first MI at an age less than 55 years old, and the controls come from the population-based MESA study. So the data I'm going to show in a pictorial format. So if you take 100 patients with MI in this data set, early MI in this data set, what we see is that roughly 2%, actually 1.7%, carry a monogenic mutation, and they're about 3.8-fold increased risk compared to the non-carriers. One more thing is that you can distinguish the hypercholesterolemia mutation carriers, the monogenic carriers, compared to the non-carriers based on their LDL. And so the carriers have LDL of 206, the non-carriers of 124. So the carriers can be identified by a genetic method, specifically the blood LDL cholesterol. Monogenic, the polygenic model, this is operative in a full 17% of the early MI cases. And so 17% of high polygenic risk, and they're about 3.7-fold risk compared to the non-carriers. In contrast to the monogenic, the high polygenic score individuals cannot be distinguished by high LDL cholesterol. The LDL cholesterol in the high polygenic group is 132, and the non-carrier is 124, so slightly higher, but not adequately so. And here, table of baseline characteristics of the group that had neither of the risks, the high polygenic risk and the FH mutation risk among the 2,000 people with early MI. And what you can see in general is that the high polygenic risk individuals, additional risk factors are slightly elevated, but not enough to be useful to identify these individuals. So the identifies 10x more individuals than monogenic mutations, but at a similar level of risk. So the prevalence among early MI cases is 1.7 versus 17. The odds ratio is similar. The mode of detection, as I said, monogenic can either be genetics or LDL cholesterol. But polygenic, the traditional risk factors will not pick these people up. They're currently unaware of their risk. You really need genotype data to understand their risk. The mechanism of risk for monogenic is elevated LDL. Polygenic, it truly is, for lack of a better word, a gamish of things, millions of variants. Then the question becomes, well, you identify these high-risk individuals potentially early in life, what can you do about it? What is intervention that you might be able to give them? For monogenic, we have lifestyle options as well as medications to lower the LDL cholesterol, and as I mentioned earlier, these powerfully lower risk. What about polygenic risk? Is polygenic risk for MI modifiable? And the answer is yes, based on work we've done over the last 3 years. Lifestyle, adherence to an optimal lifestyle has the risk among high polygenic risk individuals, and statin therapy lowers risk by more than 44%. I'm only going to talk about the statin treatment issue today, and this is work over the last couple of years where we looked at the question of do those at high polygenic risk derive greater benefit from statin therapy, and we had access to DNA data, DNA and genome data from three randomized controlled trials of statin therapy to reduce the risk of a first attack. There's DNA from enrollment into the trial. We genotyped those individuals. We calculated the score and asked whether the benefit of statin therapy varies by genetic risk subgroups, high genetic risk versus others. And what we found was among those at high polygenic risk, the relative risk reduction with statin therapy, the red bars, is 44%, and the relative risk reduction among all others was 24%. And the absolute risk reduction was also greater among high genetic risk individuals. So this really suggests that these medicines, these statin medicines, may work particularly well among those who have a high polygenic risk. And so, again, there are treatment options for these individuals. So data for coronary disease, we've also extended this approach of a genome-wide polygenic score involving millions of polymorphisms for several other diseases, atrial fibrillation, diabetes, inflammatory bowel disease, and breast cancer, and the pattern looks identical. basically those in the tail of the distribution are markedly increased risk compared to everybody else. And I'll highlight breast cancer. For breast cancer, we know that BRCA1 and 2 mutations, again, another tier 1 CDC indication, present in maybe 1 in 500 individuals, or rare, markedly elevate risk for breast cancer, maybe 5-fold to 10-fold, depending on the mutation. Here, but the majority of women with familial breast cancer do not have a monogenic mutation. Here, we see that not 1 in 500, but 1.5% of individuals may be at levels of risk to breast cancer, BRCA1 and 2, based on a polygenic model, really opening up a much larger range of women for potential more intensive screening and other interventions that have been approved to work in the BRCA setting. So let me conclude by saying that now it's possible to score polygenic components, and I've shown you the data for coronary disease and 4 other diseases, but it's really be done now for any complex trait with a large-scale GWAS study. And the scoring is done not from sequencing, but from genotype array data with imputation. It can be done simultaneously for many diseases, and it can be done at birth. And the point that we're seeing is that those in the extremes of the score are at risk for disease approaching or exceeding monogenic mutations. And for I, it's very clear that the top 5% of tail of the polygenic score is equivalent risk to monogenic mutations, and this risk is modifiable by lifestyle and statin therapy. And so I'll conclude by saying that if we care about screening for monogenic MI mutations, so it's a tier 1 CDC recommendation, we should also care about polygenic risk because it's obvious in 10-fold more individuals, and those individuals are currently not being identified prior to having a premature heart attack. And so I've tried to show you that we now have a polygenic score, a genome-wide score, where the top 5% of the distribution reliably is at higher levels of risk, similar to monogenic mutations, and statin therapy be initiated at an early age in these individuals to reduce that risk. Thank you.
Very terrific. Thank you very much. That was great. Now we will turn to Dr. Jansen, and she will be talking about using genetic risk scores in the prevention and control of common diseases, scientific and implementation challenges.
Okay, so much. I changed my title over the few days because when I was preparing this talk, I was going over my slides that I produced about this topic. Because I must say that oftentimes when I now read papers about polygenic risk, I often feel that they are problems that I think, okay, but we tackled this already in 2007, or we tackled this already in 2006. I was for the preparation of this talk, I thought, let me go back. Something's not working. So this presentation that I gave about the predictive ability, we call it clinical validity, which it is, of multiple genetic testing was in 2003 when I was invited to give a seminar at UCSF in San Francisco. This presentation, I just did finish my PhD, and I was a postdoc working on a totally different topic, evaluation of diagnostic testing, where much of the evaluation of the diagnostic test has much overlap with what we at that moment needed to do in genetic testing. So what I did in the presentation and the presentation that followed is translating from what I just learned in the prediction of non-genetic risk models to prediction of genetic risk models. But this was not but this was before that was public publication started. We were working on this topic, but others were working also before us on it. So what I will do in this presentation is cover studies from this time period, lessons learned from that time period, and then see what kind of implications they have for the things that we are doing now. So this to polygenic risk or to testing multiple genes at the same time can be found in these publications, published 1998 to 2001. I'm sure that there are more, but these were in my archives. These do have, they make a distinction between testing mutations, for hereditary diseases, going to genetic information and susceptibility for common diseases. These publications, they do not yet talk about polygenic models. In fact, the last two papers in 2000-2001 are very skeptical about the future of genetic testing, because they are saying like the susceptibility variants for common diseases, they have that strong effect as we see in monogenic diseases. So this will not going to work in practice. So they are already talking about susceptibility genes, but not yet about polygenic models. Presentation of the next publication is here from Paul in Nature Genetics, which is the first publication that did use the risk distribution. So you see risk distribution for the total population and for cases. But what they did in this publication is so they considered polygenic risk already as a distribution, that some people have a high polygenic risk and others low polygenic risk. But they did not mention how the individual variants, the individual susceptibility variants, how they could be combined to build polygenic risk models. That was done in this publication written by our host of today, Moein Khoury, and his colleagues, where this is the first paper that really describes how we can combine multiple genes into a polygenic risk. They proposed to use regression analysis for that. They several genes into the regression model and show that by combining these multiple genes, that from an average risk of 5%, people who carry one or more of those variants may find their risk markedly increased up to 90%. I made it in this paper. This it was 2003. We were still very optimistic about the effect of the risk variants. Moein and colleagues modeled risk variants that range from 1.5 to 3.5, and that generated these very high risks. So that's really the first paper that combined multiple variants into one model. This is my first step in human genetics. I'm a psychologist. I just did my PhD in risk perception, and I was just working on as a postdoc on what I said about the evaluation of non-genetic risk models. And reading this paper and reading the same formulas as seeing that Moein and colleagues wrote the same formulas as we did in our project, I saw all these similarities and also could see where the reasoning of this paper went wrong. So what we did in this to the editor is we proposed that we said, if you want to evaluate the test performance, you should not include only look at how high the risk can become in the people who carry those risk variants, but you should also include people who do not carry these risk alleles. You should use the entire population and see how well these people can be identified within that. Just had learned in the non-genetic prediction, for that to express that you calculate the area under our C-curve. So we did this data from Moein. And so these publications and many more are all from the pre-GWAS time. So the interesting thing of that is that we didn't have SNP data to work with. And from my this has two major advantages. One, the fact that we had to use simulated data to see how multiple variants could form polygenic risk models. And the huge advantage of simulated data is that you can vary all the parameters that you have to model. So you can vary the number of SNPs that you put in the polygenic model. You can vary the odds ratios of each of the SNPs, their allele frequencies. You can make the disease more rare or more common. All these parameters that normally in real data you can't vary, you can vary them in the data. And with that, you can investigate it, but also this really helps understanding what are the factors impact the predictive performance of a polygenic risk. What makes polygenic risk predictive? And of course, a very important requirement for that is that the simulation model needs to be valid, that we use. If that's the case, if it is really representing what we do in empirical studies, then the observations that you find in the simulated data, they also apply to real data as well. The advantage of doing this before the GWAS result is that we were not in a hurry. We had time to think, a lot of time to think about how to evaluate polygenic risk. We didn't have this time pressure that we needed to be the first to publish anything. There was nothing with real data, so we had time enough to think how we should evaluate these models. Learned in that time is this. So when is a risk factor useful as a screening test. Nick Walt and his colleagues had just, in 1999, published a paper where they basically say, they present the risk distributions here for spina bifida, the affected pregnancies and the affected pregnancies. And what he basically showed in this paper is a very real paper. He says, you need to have a big risk factor to be able to identify high-risk individuals among your population. And here is this, where he says there's a strong risk factor here, this maternal, something about serum that I don't know what it is. But this test really is able to distinguish the affected pregnancies from the others. This difference is not so large, and that's what you see here. There's more overlap between the risk distributions, or the serum cholesterol distributions of the unaffected and affected. When there is more overlap, it is less it's less easy to identify a high risk group. So from this scenario here, you see you need a very strong risk factor, and this is a weak risk factor. Nick Walt had already shown that if you want to have a worthwhile screening test that is worth the effort and the cost, it needs to be a strong factor. And what we see in polygenic risk, these are two early studies, one of the earliest studies about where people combine multiple variants into a logistic regression model. We see on the left, we see the distributions for the unaffected individuals, so who didn't have type diabetes, and in black you see the ones with diabetes, and here you see for age-related macular degeneration in gray the unaffected individuals, and in dark the ones with AMD. Also, if you want to use this for screening testing, you have to make a threshold somewhere above which you decide to treat people or not to treat people. You see that the risk distributions largely overlap. It is more difficult to identify a high-risk group that includes most of the patients. Whereas when the risk distributions are more separated, you see that clearly many people who will develop the disease are selected by this test, and only a small group of people who do not develop AMD. The metric that indicates how far these risk distributions are separated is the area under the curve. As the curve is low, what you see in the left, the area under the curve is the degree of separation between the risk distributions of affected and unaffected individuals. It is nothing more and nothing less. So from now, if you see an AUC value and the AUC value is close to 0.50, then you know that the risk distributions of an affected individuals largely overlap. When it is 1, which we hardly see, then the risk distributions are more separated. It doesn't tell you which levels of separation you need. Maybe 0.60 is high enough for selecting a high-risk group for diabetes. Maybe 0.76 is not high enough to select the group for AMD. It doesn't tell that. It only tells you how far are these distributions separated. The separation is not that huge. It's also not huge separation in the tail, which means that you have a lot of false positives. So how do you see? Well, you get a high AUC when you add common variants with strong effects. Here you see two risk models. One, again, the same one of type 2 diabetes, where the AUC was 0.60, and another one, the hypertriglyceridemia, where the AUC is 0.80. And what you see in this risk model is that here are the odds ratios of the variants that are included in the model. The variant in the hypertriglyceridemia model is a way stronger risk factor than the strongest one in type 2 diabetes. And the stronger risk factors gives you a higher AUC and gives you more separation between the two risk distributions. There's an exception to that rule. So you can only get a higher AUC when you have strong variants. And this is from a simulation study that we published in 2006, where we varied the number of genes that we put in the risk model. We varied their odds ratio and see which has the strongest effect on the AUC. Here, discuss only the lowest scenario, which seems the most realistic from the modeling perspective. On the y-axis, you see the area under the curve. And on the x-axis, you see a risk model starting with the 1 gene in the model up to 400 genes. And basically what this is showing is that when all the genes have an effect of 1.05, let's be optimistic, all have an odds ratio of 1.10, the AUC of that risk model is unlikely to become much higher than 0.60 or 0.70 because it goes to plateauing. And this also, I think, what Jake shows in his paper when he did the 6 million variants, if I remember correctly, the AUC was 0.64, which would be sort of predicted by this model. For alternative scenario, where we put a strong variance first in the model, and here we make different scenarios where we say, let's instead of 400 with an equal odds ratio, let the first 20 have stronger effects. And here, stronger effects, the strongest variant had an odds ratio of 3.0, and here the strongest only 1.5. But even all the others in the model had only minor effects, just a few variants with strong effects can markedly increase the area under the curve. The biggest problem, I think, what we find today, we think that most of the polymorphisms that are discovered have just very minor effects, and with the predictive performance of the risk models is also modest at best. Mostly, there may be exceptions, but most AUC are below 0.65. The AUC of genetic risk models is generally much lower than that of clinical risk models, and that when we add the genetic factors to clinical models, we see only a modest improvement, if at all. Again, there are exceptions. There are several diseases where there are a few variants with strong effects, and there you see much higher AUC. But in generally, it is very modest. Then it can be do better. And for that, you know that the quality of the prediction, so the best you can do with your prediction, is determined by the quality of your data and the quality of your prediction model. That is what we, in these days, there is most of the attention goes to the quality of the data, but the quality of the model is extremely important too, because you can only do the best with your data if you have a good model to predict the disease. If you have poor data or a poor model, then your prediction is just suboptimal. With modeling polygenic risk, and that's maybe not. Our formula for polygenic risk is very simple. We make a score where we put all the SNPs with their weights and the weights we obtain from meta-analysis or pool analysis, and that is summarized polygenic risk. But in reality, of course, the mechanisms how these SNPs interact is by far more complex. Here's for type 2 diabetes, and I'm just so very impressed that once you press on those rounded columns of items, then there is new mechanisms that unfold. And so to understand that the molecular pathways are so very complex, and what we try to do is when we make a polygenic risk score, we collapse it all to a simple weighted SIM score. And of course, this never reflects actually what is going on. I mean that it can be modeled what is going on, but we have to understand that what we are doing is huge simplification of what is happening inside us. In clinical and genetic risk model, we're doing better there. Well, also not. This is a slide from a decade ago. We explained at that time most of the when we added genetic factors to clinical risk models, mostly we find that the genes were not adding at all, and this was our explanation. The genes, they are related to, for example, coronary heart disease, not just randomly, but because they play a role in certain pathways. It is an extremely simplified version, as you see. We have that affect blood pressure, and the blood pressure cases heart disease. So each of those genes affecting pathway, and we have also genes that are related to coronary heart disease, but for which we do not know yet the pathway. No epidemiology. If you put all genes and the clinical risk factors in the model, then the genes that predispose blood pressure or cholesterol are no longer significant because their effect is represented by the blood pressure. We know this is how we investigate in epidemiology whether blood pressure is an intermediate variable between the genes and coronary heart disease. So we only find the genes that have an intermediate variable in the pathway that they affect coronary heart disease and not the others, and therefore the effect is usually very small. But what do we do polygenic risk? Polygenic risk is, to my big surprise, many articles in many diseases describe polygenic risk as an independent variable that is not related to other risk factors in the model. And I'm not sure whether that is true. At least I'm not convinced yet. And here's the reason why. Here's what we started with. But what we do with polygenic risk is the following: we combine all the genes in one risk score, then add that to a model together with blood pressure and cholesterol. But now the genes that affect blood pressure are in this massive score, and on their own are no longer, this score on its own is no longer related to blood pressure, because blood pressure genes are a small unit in here. The same as is for the other risk factors. So what we basically do is by creating a polygenic risk score, we create a variable that is no longer related to the clinical variables in the model, and therefore blood pressure, cholesterol, and all the other variables cannot mediate the effect of the genes anymore. What we then see is that we see that the polygenic risk score is not mediated by the clinical risk factors. It has its own effect on disease. And I think that is maybe an artifact. I'm not saying it is an artifact, but it might be. And I think what we need to do in the future is do a little bit smarter modeling of polygenic risk so that we give the intermediate factor, the clinical factors, the opportunity to mediate the relationship between the genes. Maybe this is just an idea. We have to create separate risk scores for all the intermediate variables, and so the rest of the genes can still add to the prediction. I think some of this is not really correct there. So can we model complex events at all? And people have seen earlier presentations of mine have seen these ships coming by. I always argue that complex events may be too complex to model because none of the disasters or none of the diseases is happening in exactly the same way. And I illustrate that with this example of the health of free enterprise, which capsized in front of Belgium in 1987, where on a very clear day, there was nothing wrong with the ship, nothing wrong with the staff. The ship capsized within 100 meters from the coast. And we analyzed, with hindsight, is trying to explain why the ship capsized, and they came to the conclusion there were multiple factors at the same time. For example, bow doors at the back of the ship, these ones, they were open because someone had fallen asleep. They had full ballast tanks to get cars on the upper deck of the boat. The open door was closer to the water. And because they were delayed, they had higher speed and creating higher waves that could enter the boat because it was low on the water and with an open door. And that is how the water entered the ship and the cars started to imbalance. So this is how then people analyze that in disasters. They create a complex diagram to find out what are the risk factors, the unique risk factors contributing to this disaster. And I always argue that for complex diseases, we all have our own complex model, and it may be so each develops the complex disease in their own way, which may be very, very hard to model it in an accurate way. Well, just a little bit that learned in the beginning of in the pre-GWAS days was how to evaluate genetic tests. This is the famous ACE model developed by Balamaki for the evaluation of genetic tests, but which easily can apply to polygenic risk scores as well. It's a very comprehensive framework that shows that it's not only the analytic validity and not only the clinical validity that determines whether a genetic is useful, but you have to put other context factors in place. We're in the middle of the wheel. The key aspect, what is so important in prediction, the disorder and setting. What's predicted in whom and for what purpose? Just as what Sek said. Every change to this disorder and setting changes the evaluation of the performance of the genetic test and its utility. And so that makes it very difficult to translate, to find what is useful in one setting may be useful in another setting because many of these other parameters change as well. I find it so very important because what we see too much these days is that claims about utility or that a risk score might be useful for screening are too often based on the statistical significance of the polygenic risk score only. And I think it is time now, 2018, to become a little bit more comprehensive in that. Also look at the context of the genetic risk score, whether it can be useful for the prediction of diseases. I'll come back to that in my last slide. So this is a paper from 2008, building on the work of what they did in 2002. Is, for example, when you have polygenic risk for breast cancer, when you do polygenic risk scores, you will find that some women have a higher risk than others. And what Pedro and colleagues propose is that you can start at an earlier date of screening for the women in the highest percentiles of risk, maybe skip the screening even for the ones in the lower percentile of risk. And what is interesting of this approach is that in these days, in 2008 and before, we were very focused on keeping the healthcare costs the same. We were very much focused on redistributing efforts. So with some people you do more intensive care, and with others you do less care. And what we see now very often is that we propose new care to the highest risk group, and we need to be very vigilant there to keep whether that is affordable. We cannot keep increasing high healthcare costs, even though it is very important to prevent disease. The other is changing health behavior. We know from past studies that there's little evidence that people have that long-term impact on health behavior, but we have to be clear there. Most of those tests that were investigated were very simple tests or very simple risk scores. We don't know yet whether when the polygenic risk scores become more sophisticated and really predictive, whether it will impact people's behavior. But then I foresee when we do that in the future, it will not be one risk score that the patient gets, but they get them for every disease. And that is reflecting what Tina et al. Already said at the time. You have values that increase the risk of one disease and decrease the risk of others. And I expect that later people also get polygenic risk score reports, not only for one disease for which they may have a higher risk, but at the same time they have a low risk for diseases that are maybe affected by the same behavioral response. For example, if you need to keep a healthy lifestyle to reduce your cardiovascular disease risk, and if you have a low risk for obesity, it becomes really challenging to motivate these people to a healthier lifestyle. Okay, this is my last slide. I think in 2018, having already 2 decades of risk research behind us, I think we need to get it, make it a bit professional. I think it is very important to improve the modeling to better reflect the underlying mechanisms. I expect if we that we increase the predictive performance of polygenic risk scores when they are applied alone, but that it may reduce their value when they are added to clinical risk factors. I think that we should adopt a more responsible approach to the assessment of the potential utility of the scores, because it's not only the statistical significance of the association that is relevant. We need to be sure that we assess the performance of the risk scores in the target population that we want to use for, as Sek summarized so nicely. We need to apply the appropriate performance metrics for prediction and not for association. And we need to be aware of the context of the prediction, whether the predictive performance is high enough, whether it's actionable, whether it's affordable if we are proposing additional care. And also, it needs to be better than what we already have. It needs to be compared with the available non-genetic risk models. I think this would be my most important point for moving forward in this very exciting area. Thank you.
Thank you much. This is Moeen Khoury, Director of the Office of Public Health Genomics. I'd love to thank Sek and Sil for a very stimulating discussion. For those of you who are joining this webinar, please type in your questions. We have maybe 15 to 20 minutes for further discussion. As well, if you're on Twitter, hashtag GRS webinar. I must say that we've been doing these webinars for now almost 2 years, and this by far is the most popular webinar in terms of interest of people who signed up. We had more than 300, I guess, by last count, as well as some of the dialogue on Twitter that I've witnessed over the last month. Now, I don't know where to start. This is a very vast subject. I can subscribe to both the opportunities and the challenges, but I felt like Sek has us at the beginning with a very specific clinical scenario, which is the prevention of attacks in young people, because he thought that risk factors don't work well. I guess the equations that people use for predicting heart attacks. So I'm taking this to heart. I'm trying to see how we can navigate forward. I understand all the complexities that has laid out in front of us, but I would like to kind of start the discussion with the specific scenario that Sek has laid out in front of us. So we about Tier 1 applications. Obviously, it was a direct challenge to us. We care about familial hypercholesterolemia and using genetics to reduce burden of heart disease and cancer. So the analogy with the Tier 1 is that right now nobody is doing population screening to find with FH at the genetic level. So that's sort of the Tier 1 application comes when you have an FH patient. It's about cascade screening to relatives. So the population screening is just using cholesterol to and the MedPet criteria or the Dutch criteria or whatever criteria you want to find that first case, and then you do the cascading. Now there are people would love to do population screening for FH at the genetic level, measure the mutations in these things. So that Tier 1 application scenario doesn't work very well, because we're going to screen everyone for the polygenic risk scores that predict MI. Do we start there, or do we wait for them to develop high cholesterol or high blood pressure? So the question is for sake here, and specifically about the interventions that are available, because you've showed us very nicely that these people at the top 5% have a high risk. Now, you also showed us that many of them don't even have high cholesterol. So are we starting people on statins and giving them a physical activity regimen? So that's a very specific question, because it's very specific to a unique scenario that you've laid in front of us, because I'm intrigued by it. I would love people to weigh in on it, and there are many other questions that come in. So say, what's your response to the challenge about what to do with a genetic risk score in people in the absence of the other risk factors? What are the interventions? Do we put on statins even though the LDL is low? What do you think?
Yeah, a couple of points. One is these individuals that, a bunch of people who have heart attack at a young age, the fact is only about 2% of them do they have FH, okay? So what's going on with everybody else? And it's very clear now, at least in 20% of those additional individuals, so tenfold more higher, the one major factors is the polygenic model. So we've clearly established that in multiple studies now. So then the question becomes, okay, you have a group of people who are having a heart attack at a young age, with the polygenic model playing a large role, and how to find them, and what about it. What I show you was that I can't find them right now based on other risk factors, because they don't have higher blood pressure, don't have higher cholesterol, they don't have higher diabetes, they don't even have that much higher family history. So they're hidden now, and they largely show up when they have the first heart attack. So the thing, though, and you can find them, of course, using a chip with imputation and calculating a polygenic score. If you find them, what can you do about it? I think that's an open question, and I don't think we know, we would know a priori that this risk was modifiable, but actually published a handful of studies that show that the risk is modifiable by lifestyle, which, you can argue should be given to everybody, but it's to know that lifestyle can modify if you happen to be high polygenic risk. But more importantly, intervention that is not going to be given to everybody when they're young, which is statin therapy, that modifies the risk. Despite the fact, as you're saying, Muin, that their start LDLs are population average. I wouldn't call it normal. It's in 130. But LDL down from 130 to much lower markedly reduces the risk, almost half. So we have an intervention that's been proven from, secondary studies of completed statin trials that statins that can be given to these people at high polygenic risk. I think this is, kind of a best case scenario for this approach. You have a lot of people at risk. You're not identifying other ways except to show up with a heart attack. You can find them with a relatively cheap test, and you have something you can do about it. So I think that there's this is a pretty good scenario to pursue. Okay.
You can say about people with family history who, as said, are not picked by genetic risk scores. That applies to across the board: cancer, heart disease, people with early onset family of, let's say, breast cancer cancer, ovarian cancer, etc., are also at increased risk. You identify them by a simple question, and you may or may not modify the approach. But plenty of questions came in, but to see what you try to answer, say, directly on this approach, what do we need to have in terms of knowledge, able to apply, take specific scenario in order to evaluate the clinical utility of a genetic risk score for early attacks? What kind of information? Do we need a de novo clinical trial, randomized trial, or what do we do? What kind of information?
Well, what I would need to be convinced is a very basic cost-effectiveness study. Because what worries me still is that, especially in the younger population where the risk is so very low, if you select there 17% of the people, you will have enormous number of false positives that you put on statins without them benefiting, and maybe they benefit for other reasons or for others that I don't know, but that's my first. I see the optimism, I see the reasoning, but I'm not sure whether it will hold in a formal analysis.
Sorry, it's 5% of the population, 17% of the kids.
Yeah, but it's still 5%. So if the risk is very low, then it's still a lot of people that you put on statins where they will not benefit.
Okay.
That would be, but also even before we put them on that risk, if majority of people in the highest risk group will not develop the outcome, then I'm not convinced that it can be a very efficient approach. But
that's for Mendelian mutations as well. You know, the positive
value.
Yeah,
no, I got that. So I think what Moeen was. I want to thank you, Sek, for making that point about the model driven by age. That is my biggest point with most prediction models in clinical practice. That if you develop a risk model in a population that varies from 50 to 80 years, then age is always the biggest predictor, and it's useless for young people. Thank you for making that. But I think that the comparison that you made with the tier 1, I think is a tier 1 because it is a cascade screening program, not because it is a population screening program. And so because of the cascade screening for the missions, when you find someone, you also find their relatives, and the benefits are much more beyond one individual.
Right.
So that's what you.
You're finding that. You find them, okay? If in them, why do you care? Why do you care? It's only because of a relative increase in risk, and relative increase in risk is very modest. It's fourfold.
I want to interrupt here. This is Moeen. I think we can spend the next hour debating this, and we should. But I wanted to read all the questions because they're very interesting. Come in. Before I do that, there was some reference to Paul Farrow and the work that was done in the UK about cancer screening, and that work continues. A couple of years ago, the NCI held a workshop that we sponsored here about risk stratification and cancer screening. That's a bit different maybe than treatment with statins, but that work continues still now. Nora Pashayan, who was the first author of the paper that came out of our workshop a couple of years ago, we discussed risk stratification, genetic risk scores in the context of breast cancer, prostate cancer, and a lot of the debate around cancer screening. And that whole scenario, actually, you can use the whole distribution. Think about potential interventions or lack thereof, let's say a very low-risk population. If you go to the other 5%, the curve where, the benefits of population screening, let's say for breast cancer at a certain age may not be there if you have a low genetic risk score. So when you have a score, you have to think about the whole distribution, not just the upper 5%. That's the background. But let me read to you a few questions here, and I'll probably run out of time. I'm stacked here. People have asked a number of methodological questions about best ways to compute SNPs and risk scores, overlapping data sets, harmonization, standardization, validity and accuracy beyond, let's say, non-European population. Most of the genetic risk scores and GWAS have been done in non-representative populations. So if anyone, if you want to kind of give us just a quick flavor of some of the methodological challenges, because I can't assume that the genetic risk score is as easy as measuring cholesterol right now, or LDL cholesterol. It's a bit more complicated. So, Sek and Cecile, you want to say a few words about the harmonization and standardization of genetic risk scores, generalizabilities, and so on and so forth? Take you first.
Yeah, that's great. Thank you. Yeah, I'll take one issue. The one issue that I think is quite relevant is the generalization of these scores across ancestries. And so we looked at this. The fact right now is that I think more than 8% of the world's GWAS data is done in individuals of European ancestry, and therefore the scores, specifically for coronary disease, largely come from GWAS done in whites. So it's a surprise that the scores derived from those GWASs essentially work best in whites. And so we've looked at this, the same genome-wide polygenic score in multi-ethnic study. I mentioned the Virgo study. You look at the top 5% of the distribution compared to everybody else, the odds ratio for whites is 5, LEMI. The ratio for Hispanics is 3.4, Asians is 3.3, and blacks is 2. So every group, the same score is predicted. The same score largely derived from GWAS and whites is predictive, but the magnitude of effect drops off basically the further away you are from European ancestry. So there are a couple of ways to think about that, how to communicate information. But this is not something that where medicine is new to. For example, the Framingham risk score that's been used in clinical practice for 50 years was derived from 3,000 whites in the town of Framingham from 1948. So, and used in every ethnic group in the United States for many, many years. And so I think to improve these scores, but I think so let me just stop there.
Cecile, if you have something more to say about this, I want to ask you one specific question, which is has been in my mind for a long time, and one of the people have asked it. So somebody has been saying that your presentation misses the point, that EUCs does not tell the whole story about utility of genetic risk score because does not take into account the absolute risk of disease. Disease and breast cancer are fairly common. The genetic risk score provides important risk classification even when the AUC is modest. I know you and I have had that discussion over the years. Can you tell us what you really think about AUCs versus absolute risks?
Yeah, absolutely. And I think I get the impression that this question, who I know, mislies about AUC, because I said AUC is only assesses the degree of separation between the risk distribution of affected and unaffected individuals, nothing more and nothing less. And I totally agree that sometimes a modest AUC can be high enough. For example, if you want to improve breast cancer screening, mammography screening program, you want to make it more efficient by assigning women at higher risk, inviting them a bit more frequently or at earlier age, and the women at a lower risk a bit later, more infrequently. To this stratification of a population screening program, the age does not need to be that high. And when you want to recommend prophylactic surgery to women based on polygenic risk, the AUC cannot be high enough, because we don't want that women make a decision based on a polygenic score. And so the level of AUC is high enough, totally depends on the context, the purpose of testing, and the evaluation of the harms and the benefits. So the AUC is a frequently misused metric, but at the same time, it's at the core of prediction, because it simply describes the degree of separation between the two risk distributions, nothing less. You know that I'm a big fan of AUC, so I'm a little bit biased.
Okay. Second, you want to add to that? You don't have to. Okay. So this dichotomy between monogenic and polygenic risk is still on my mind because we have to find ways to operationalize these concepts. I mean, fast forwarding to the future when, let's say, we have a situation like in some systems where they're beginning to do whole genome or whole exome sequencing on everyone, like Geisinger and maybe Kaiser and other groups. So the question for both of you is, what do you do when you have the whole genome in hand for a variety of purposes? Do you, right now, for example, there is a recommendation from the American College of Medical Genetics and Genomics to return the results of seeing information on 59 genes. These are mostly monogenic conditions like Lynch syndrome and BRCA. What do you do with the genetic risk scores in the context of biobanks or clinical biobanks that have been laying around where you could return the results of a polygenic risk score? What do you do with it, and how can you study it in the context of a research to identify its clinical utility moving forward? So who wants to answer that?
Yeah, I can take a crack in there. Yeah, no, it's not a straightforward path in the sense that what's important is to find a scenario where you can identify a subset of individuals at meaningfully elevated levels of risk. But in addition, you need some intervention, pair that risk with an effective intervention, either screening or treatment. In scenarios, you can start considering thinking about returning polygenic risk like you return DMG59. I mean, again, I don't mean to keep harping on this, but the only reason we return LDLR, ApoB, PCSK9, those three genes among the ACMG59, because mutation carriers have an increased risk of heart attack. I'm trying to show today was that it turns out 5% of the population has a similar increased level of heart attack to those mutations. And this scenario, I think it'd be it's varied by disease and intervention.
Thoughts on this?
Yeah, I think we are definitely moving in that direction. But what worries me most is that we will start applying polygenic risk without the proper evaluation, because even when it's free and available and people wanted to have it, if the tests that we are using for each disease and each purpose is not predictive enough, we are making healthcare very, very inefficient and increasing costs more than we want to. And, so I hope that there will be procedures in place to prevent that from happening. Because free, it doesn't mean that that's informative.
Yeah,
so, final question to yeah, go ahead, say.
Totally, Cecile, and it's actually been interesting to watch the ACMG list being returned, and from thinking, is it worthwhile, trying to prove, is it worthwhile to return this information? Their return essentially improve health outcomes to very now where people are saying, could you not return that information with the intermediate of actually demonstrating that kind of return acts people better in some meaningful way, So I agree with you. I think it's very important to think through what the health outcomes are when you do kind of return.
So question to both of you, and we have to break soon. So please help us put the polygenic risk scores in the context of other known disease risk factors. So if you take heart disease, cancer, breast, ovarian, the idea that genes and environments interact and increase risk is an idea we've been seeing around for too long. So focus on genetic risk scores should not negate the fact that the individual total risk for a particular disease is more than that individual's just genetic risk score analysis. So how would we square that in our population screening efforts as well as individual medicine efforts, because I'd like give us the final say for both of these things. Let's say you go first.
Yeah, I think most people desperately want complex diseases to resolve into simple subsets. Bottom line is complex diseases are complex, and they really literally are the interplay of many, many common variants. Some people have mutations, lots of lifestyle factors, and I think coronary disease is a great example. It's very clear that a range of variables can be into model, some genetic, some non-genetic, and they kind of play an important role in understanding one's risk. And so I think that's true for the full spectrum of complex diseases. What we're better now is quantifying that susceptibility from the polygenic side than maybe a few years ago. And that would change, I think, in the last couple of years.
Okay, last word, Cecilia.
Yeah, I think what I find most interesting to watch for the coming years is to see how the polygenic risk scores are going to change. I think that we are still in the very, very early stages of polygenic risk research, thinking about the modeling. I think we have all really adopted a very simple approach of weighted risk scores. I wouldn't be surprised if we do a little bit more sophisticated modeling and a little bit more thinking about how diseases are being caused, what mechanisms are behind it, that maybe even the polygenic risk scores get even more predictive. And what you then see, of course, that people who were initially at high polygenic risk might with a new and a better modeling come at moderate genetic risk or even low. So that is how I'm. That's one of the things that I'm looking forward in the coming years. Yes.
So with that, I'm going to thank both of you, our shares, and the more than 200, 300 people who joined us today. Please continue the conversation on Twitter, #GRSWebinar. This has been a great discussion today, and I don't really think we have too much. I mean, I thought that it will be so far apart in our way of thinking, but science prevails at the end of the day, and I think we all need the scientific foundation for using genetic risk scores in both medicine and public health, and for that, we can thank both our speakers. So with that, I'm concluding our webinar for today, and thank you all for joining us.
Thank you, Cecile.
Much.